Hi all. In today's class, we'll discuss about general organic chemistry. We'll begin our class by discussing what is acids and bases. Mainly, there are three theories to explain acids and bases. The first one is Arrhenius theory, and the second one is Bronsted-Lowry theory, and the third one is Lewis theory. So we'll start by discussing what is Arrhenius theory. So according to Arrhenius theory, acid is a substance which will increase the concentration of H plus ion in aqueous solution, and base is a substance which will increase the OH minus ion concentration in aqueous solution. Here, Arrhenius explained both acids and bases in aqueous solution only. Okay. Now we'll discuss Bronsted-Lowry theory. According to Bronsted-Lowry theory, acid is a substance which will donate H plus ion, and base is a substance which will accept H plus ion. Okay. Here, the Bronsted-Lowry theory is applicable to any protonated solvent. Now we'll discuss about Lewis theory. In Lewis theory, acid is a substance which will accept electron pair, and base is a substance which will donate electron pair. Okay. So here, Arrhenius explained acids and bases as acid substance which will increase H plus ion concentration, and base substance which will increase OH minus ion concentration in aqueous solution. Okay. Bronsted-Lowry theory, acid is a substance which will donate H plus, and base substance which will accept H plus. And Lewis theory, acid is a acceptor of electron pair, and base is a donator of electron pair. Okay. Now, if you have to compare these three, Arrhenius theory is only explaining in aqueous solution, but Bronsted-Lowry theory is explaining what is acids and bases in any protonated solvent. So compared to Arrhenius, it is a more general explanation of acids and bases. But Lewis theory is explaining what is acids and bases in every reaction where there is electron involvement. So in these three, Lewis theory is the most wider explanation of acid and bases. Then Bronsted-Lowry theory. Then comes Arrhenius theory. Okay. So if you have to sum up these three theories of acid and bases, we can say that acid is a substance which will donate H plus or accept electron pair, and base is a substance, whatever is acid, then base will be the exact opposite. So here base is substance which will accept H plus or donate electron pair. Here we can say acid is donator of H plus and acceptor of electron pair. So this only we have to learn. Base will be the exact opposite. Here, if acid is donating H plus, base is accepting H plus. If acid is accepting electron pair, then base is donating electron pair. Okay. So now we'll explain two terms. And here I am taking an acid here. And acid is a substance which will donate H plus. So there is a hydrogen in our molecule, that is an acid molecule. And suppose this acid is losing a H plus. So what we will get? There is a H bond in our molecule, and this bond is breaking and H plus is leaving. If H plus is leaving, that means this bonding electron is moving to A. So in that case, we'll get A minus. So if you are having an acid, after losing H plus, we'll get a negative charged species. So first we have an acid, and acid is losing an H plus, and we are getting a negative charged species, which is a base. We'll call this base as conjugate base. So from acid, we got conjugate base by releasing H plus ion. Okay. This will happen in case of base also. So base is a acceptor of H plus. So suppose B's are base and B is accepting H plus ion, that is proton. What we'll get? We'll get BH plus. So initially we had a base and accepted H plus. Now if you are looking at the end result, we got a positive charged species. A positive charged species means it will be an acid, and this acid will call as conjugate acid. Okay. So from base, after accepting an H plus, we got an acid which is called conjugate acid. Okay, now we learned two new terms. From acid, after losing H plus, we will get conjugate base, and from base, after accepting H plus, we will get conjugate acid. Okay. So now we'll explain two terms, Ka and pK, which will help us to identify the strength of acids and bases. Here, Ka is called acid dissociation constant. Okay, Ka is acid dissociation constant. So to explain this, we'll take again the acid H, and H is dissociating into A minus and H plus by releasing of a H plus ion. After releasing H plus, we have told that we'll get A minus, which is a conjugate base of acid H. Here, this reaction will exist in equilibrium. That means here both forward reaction and backward reaction will happen at the same time. In that case, we can explain this reaction in terms of a dissociation constant Ka. Ka will write in terms of concentration of product by concentration of reactant, right? So here K will be concentration of A minus into concentration of H plus, which is the product here, A minus and H plus, divided by concentration of reactant, that is H or acid. So if you are looking in this equation, suppose H is a very strong acid. That means the forward reaction will happen fast. That will lead to the release of A minus and H plus more. So if our H is a strong acid, it will result in the higher concentration of A minus and higher concentration of H plus. And it will lead to the low concentration of H. If you are looking at K, if our acid is strong, then we'll get high concentration of A minus and high concentration of H plus and low concentration of H. So it will lead to the high value of K. That means if you are having a strong acid, we will get high Ka. Okay. Now we will see in terms of pKa. Here pK is equal to minus log Ka. So from this equation we can see Ka and pK is having inverse relationship. That means if Ka is high, then pK will be low. Ka and pK are in inverse relationship. So that means we already seen strong acid means we'll get high Ka. So that means since pK and K is in inverse relationship, high Ka means low pK. So for the strong acid, we'll get low pK and high K. This we have to remember. And now we'll discuss in terms of base also. So we have told whatever happening in case of acid will be opposite of whatever happening in case of base. So acid, we have seen for strong acid, we'll get high Ka and low pKa. So in case of base, the opposite will happen. So for a strong base, we'll get low Ka and high pK. Okay. Now we'll write the every relation that we have learned so far together. Suppose we have a strong acid and strong base. So strong acid means high Ka and strong acid means low pK. Okay. And for base, the opposite of this, that means for strong base, we'll get low Ka and high pK. Okay. So this is what we have to see in terms of Ka and pK. High Ka means strong acid and high pK means strong base. And we'll only learn in terms of acid because whatever we are learning in acid, we can take just the opposite in case of base. So for a strong acid, we will get high Ka and we'll get low pK. We will learn this, okay? For strong acid, we will get high Ka, low pK. So for base, the exact opposite will happen. So this is what we have to explain in terms of acid and bases. So we have seen for a molecule to be strong acid, we should get high Ka and low pK, okay? So in exam, the question will be asked like from given compound, which is the strongest acid. In that case, what we have to see is, we have seen for an acid, Ha, it will release an H plus and we will get A minus, and this A minus we called as conjugate base. Okay. So suppose in exam question is asking like from given compounds, which is the strongest acid. What you have to see is, we have to see the corresponding conjugate base of the acid and we have to see the stability. Suppose our conjugate base is stable, That means we have very strong acid. Okay. So to check the acidic strength of an organic molecule, what you have to see? You have to see the corresponding conjugate base, and then we have to see the stability. If it is stable, that means we are having a strong acid. And one more point is that suppose we have a ketone in our molecule, organic molecule, that means the CH2 adjacent to ketone, that is this CH2 is so much acidic. Why? Suppose we have a ketone and this carbon, there is 2 CH bond. Suppose we are losing a H plus from this, and if you are losing a H plus, what you will get? The remaining will be a negative charge in this carbon. So if we are getting a negative charge here, there is a chance of delocalization. This negative charge can move here, and this electron can move to oxygen, and at the end you'll get a structure like this. And this negative charge in case is very much stabilized due to this conjugation. That's why this is acidic proton. Because as we have seen here, for a compound to be acidic, after losing a proton, the resulting conjugate base should be stable. And here this molecule is very much acidic because after losing a H plus, we are getting a conjugate base structure like this. And this conjugate base, the negative charge is delocalized. That means this is stable. So since this is stable, these two CH bonds are very much acidic. If a ketone is present in molecule, that means the adjacent CH2 groups are acidic. Okay. So now we'll discuss about basicity. So base we have already explained. Base is substance which can accept H plus or donate electron pair. Right? So suppose we have to see the basic strength. There is two ways. Either we can see the availability of electron pair. This is the first way. The second way is that after accepting H plus, we have seen base will accept an H plus, and after that we will get BH plus, and from the base we will get a acid which is called conjugate acid, right? And the second way is that we can find out the stability of this conjugate acid. Okay, so there are two ways to check the basicity of the molecule. The first one is checking the availability of electron pair, and the second method is checking the stability of resulting conjugate acid. So now we'll find out how to find the basicity of two compounds and how to compare the basicity of two compounds by using an example. Here the question is, out of these two molecules, which molecule will protonate first? So in this question, we have given two molecules. In both these molecules, we can see nitrogen atoms. And we know in nitrogen, there will be a lone pair. And we have to see which molecule will protonate first. That means, suppose we have given a proton in each case, which molecule will donate its lone pair to the proton in fast manner. If a molecule is donating its lone pair, then it is base, because we have seen the definition of basicity as donation of electron pair. So here nitrogen, as you can see, is donating its electron pair. So both these molecules are basic. And the question is, which will protonate first? That means which molecule is more basic? That is the question. Here both are nitrogen, and both we can see lone pair also. The only difference is that in first molecule we can see 3 sigma bond in nitrogen. That means it is sp3 hybridized. In second molecule we can see a double bond in nitrogen. That means it is sp2 hybridized. So we know in any atom there will be a nucleus which is positively charged, and then comes the s orbital, then p orbital, then there is d orbital, right? So we'll denote the first orbital as S, then comes P, then comes D orbital. Suppose there is an electron in S orbital, an electron in P orbital, and electron in D orbital. We know the S electrons are closer to nucleus. So that's why the S electrons will be attracted to nucleus more, and P electron compared to S electrons somewhat far from the nucleus. So that's why P electrons are attracted by the nucleus but not as the same extent as of S electron. So if you are comparing both, s electrons are strongly attracted by nucleus. That means if you are comparing the donor ability of both s and p electron, the donor ability of s will be less compared to p. So the donor ability of p is more. Now we are looking at the hybridized, different hybridized orbital. We have sp hybridized orbital, sp2 hybridized, sp3 hybridized. In sp hybridized, how many orbitals are participating? S and p participating. So total 2 orbital. In sp2 total 3 orbital. In sp3 total 1 s and 3 p. So total 4 orbital, right? In sp orbital, half, that is 1s 1p is participating, so s character will be half of the total, so it will be 50 percentage s character and 50 percentage p character. In sp2 hybridized, out of total 3 orbital, 1 orbital is s, that means 1 by 3 s character, 2 by 3 p character. So 1 by 3 s character means 33 percentage s character and 66 percentage p character. Okay. In S3, 4 orbitals are participating, and out of 4, 1 orbital is S orbitals. That means 1 by 4 S character and 3 by 4 P character. That means 25 percentage S character and 75 percentage P character. Okay. So if you have to compare this SP, SP2 and SP3 orbitals, you can see in sp hybridized orbital, there is 50 percentage s character. In sp2, there is 33 percentage only. In sp3, there is only 25 percentage s character. So here we have seen that s electrons are having less donor ability compared to p electrons. P electrons will donate fast. That means that higher the s character, it will lead to lower the donor ability. Okay. So out of these 3 orbital, that is sp, sp2 and sp3 orbital, sp3 orbital will have high donor ability because here we can see there is only 25 percentage s character, and out of this sp orbital will have the least donor ability because here there is 50 percentage s character. Okay, so this will be the order of donor ability of hybridized orbitals. Now we'll come back to your question. In our question, we have given 2 nitrogen. One is sp3 hybridized and one is sp2 hybridized, and the s character is more in sp3. That means the donor ability is more in first molecule compared to second molecule. So first molecule will protonate first. Okay. Now we look into a second example. Here also the same question. Which will protonate first? In the same molecule, we can see 2 nitrogen, and out of these 2 nitrogen, which will protonate first if we are giving a proton in this molecule? Okay, that is our question. So if we are looking again, 2 nitrogen are present in this molecule. So in nitrogen, a lone pair is present. This lone pair can donate to this proton, and in that case, this nitrogen is acting as a base. So we have to see which nitrogen is more basic. The more basic nitrogen will donate its lone pair fast to the proton, and it will protonate fast. So again, if you are looking at the hybridization, here this nitrogen is having a double bond. So that's why it is sp2 hybridized, and this nitrogen is having only single bond. So it is sp3 hybridized. In last question, we have seen that sp3 is having more donor ability compared to sp2. But here, one more thing is present, that is here a delocalization is present in this molecule, because here a lone pair is present in this, and adjacent to this lone pair, a double bond is present. And if a double bond and a lone pair present, that means this lone pair can take part in the conjugation. That means this electron will move here, and this double bond will move to this nitrogen. And from this structure, we will get structure like this. Now a double bond will come between this carbon and nitrogen, and a positive charge will come on this nitrogen. If you are looking at this nitrogen, there is no lone pair because that lone pair took part in the conjugation and formed a double bond between this carbon and nitrogen. But the second nitrogen, that is this nitrogen, the lone pair is still there. This lone pair is not taking part in the conjugation. In this molecule, there are 2 types of lone pairs are present. that is this lone pair and this lone pair. Here, the first lone pair, that this lone pair can take part in the delocalization. The lone pair which is taking part in the delocalization, we'll call that delocalized lone pair. And then here, this lone pair which is not taking part in the delocalization, we'll call it as localized lone pair. Okay, here this is delocalized lone pair and this lone pair is localized lone pair. So the first criteria we have to look in a molecule while finding out basicity is that looking for delocalization. If delocalization is present in our molecule, then that localized bond will have high basicity. Okay, this is the first criteria. The second criteria only, if all bonds are either delocalized or localized, then the second criteria only we look at the hybridization. So the second criteria is hybridization. So hybridization we have already seen. sp3 hybridized orbital is having more donor-ability than sp2 than sp. So we are coming back to our molecule. So molecule again, two nitrogens are there. In both this nitrogen, lone pair is there. But this lone pair can take part in delocalization. But this lone pair is localized lone pair. So if delocalization is there, then we have to give priority to localized lone pair. So this is more basic in our molecule. That means this nitrogen will protonate first. Okay. Now we look into the next molecule. In this molecule also, 3 nitrogen atoms are there. So all these 3 nitrogen lone pair is present. So if you are looking at hybridization, we may think both these are sp3, this is sp2. So sp3 is having more donor-ability than sp2. But first, I told you, first you have to look for delocalization. So if delocalization is present in our molecule, we have to look for localized lone pair and that will have high basicity. Okay, so in our molecule, we have to look for delocalization. Here we can see a double bond and this two lone pair can take part in the delocalization. That means this lone pair can take part in delocalization like this, and this lone pair can also take part in the delocalization like this. So both these lone pairs are taking part in delocalization. That means the lone pair which is on the sp2 carbon, which is not taking part in any delocalization, that is localized lone pair, will have high basicity. So in this case also, the lone pair on the sp2 carbon, which is localized, will have high basicity. Okay, now we'll move to the next molecule. In this molecule, here we can see both nitrogen atom is there and oxygen atom is there. And we know in oxygen atom, there is 2 lone pair in oxygen and there is 1 lone pair in both these nitrogen. And if both nitrogen and oxygen present in our molecule and both of these having lone pair, and in this case, nitrogen will have high basicity and nitrogen will be donating its lone pair to the proton because compared to nitrogen, oxygen is more electronegative atom. So due to high electronegativity of oxygen, this oxygen having low tendency to donate its electron pair. So due to low tendency of oxygen to donate its electron pair, the nitrogen which is having less electronegativity compared to oxygen will be more basic. So in our molecule, here we can see nitrogen and oxygen. Since oxygen is having high electronegativity, it is having less tendency to donate its electron pair. So nitrogen will donate the electron pair. So either this nitrogen or this nitrogen will be more basic. Now we have to determine out of these two nitrogen which is more basic. Okay. So the first criteria is always looking for the delocalization. In both this nitrogen, we can see the lone pair. Here, this lone pair is not taking part in any delocalization. It is localized lone pair. Now, if we are looking at this lone pair, we can see a double bond adjacent to it. So, this lone pair can take part in the delocalization. That means this nitrogen which is having a localized lone pair will have high basicity and it will accept the proton. In this molecule, this will be more basic nitrogen. Now look for this molecule. In this molecule, we can see oxygen and nitrogen. Here we can see both sp3 hybridized oxygen, sp2 hybridized oxygen, and sp3 hybridized nitrogen. Right? And we have seen already, if both oxygen and nitrogen present, then the basicity of nitrogen will be more due to the electronegativity of oxygen. So we don't have to consider the oxygen atoms here. We'll only look at the nitrogen. Now there are two nitrogen in our molecule. This nitrogen is sp3 hybridized. This nitrogen also sp3 hybridized. Now first criteria is that we have to look for delocalization. This lone pair is not having any adjacent double bond. That means this is a localized lone pair. But here, this lone pair is having adjacent double bond. That means this lone pair can take part in the delocalization. So this lone pair is delocalized lone pair. So in this case, this nitrogen will have high basicity and this will protonate first. Okay. So what we have discussed till now? So to determine the basicity of two atoms in a molecule, what we have to look for first is delocalization. If delocalization is present in a molecule, then the localized lone pair will have high basicity. If there is no delocalization, then we look for hybridization. Okay. In hybridization, the sp3 will have more donor ability than the sp2. Then comes sp hybridized orbital. So now we'll discuss a question from acidity and then we'll move on to next topic. Okay. It is a previous year question. The question is the correct order of acidity of compound A to C is. And we have given here the three compounds from A to C. So we have seen to find the acidity of compound, what you have to do? We'll remove an H plus from molecule. Then if we're removing an H plus, suppose we have a molecule like H and the molecule is losing an H plus, the remaining we'll get A minus and the A minus we called it as conjugate base and we have to find the stability of this conjugate base. If the conjugate base is stable, that means our H is strongly acidic, right? That we have seen. So in this three molecule also we have to do the same. We have to remove H plus from each of this molecule and then we have to find the stability of the remaining conjugate base. So first we'll take the first molecule A. This is the compound A. Here we can see two carbonyl group and there is a CH2 group in between. This is strongly acidic. You may be getting confused like this also CH2, this also CH2, this also adjacent to a carbonyl group and this CH2 also adjacent to this carbonyl. But here this CH2 is only adjacent to one carbonyl. Here this CH2 is adjacent to only one carbonyl. But here this CH2 is adjacent to two carbonyl group. That means this is strongly acidic CH2 group in this molecule. So the proton will lose from this carbon. Suppose we are losing a proton from here, we will get a negative charge in this carbon. So the resulting molecule will be like this. There will be a negative charge in this carbon. So it is from the first molecule. Like that, we will get corresponding conjugate base from compound B and compound C. From compound B, how we will get? There is a phenyl group here and the same manner, we will lose a proton from this carbon, we will get a negative charge here. And in compound C, which is the most acidic proton, these two protons are most acidic. Why? Because here we can see OH bond and OH bond is strongly polar. That means due to the electronegativity of oxygen, this bonding electron will be strongly towards oxygen. So this bond is strongly polar. So the hydrogen will lose from here only. So after that, the resulting structure will be from compound C. There's two ketone and one of the OH will lose a proton. Earlier it was like this and we lose a proton from here. If we are losing a proton, then this bonding electron will move to oxygen and we'll get a negative charge in oxygen. So the resulting structure will be like this. And out of these three, we have to see which is the most stable one. That will be the strong acid. Here in both A and B, the negative charge is presenting on the carbon. But in C, the negative charge is on oxygen. So, oxygen is electronegative compared to carbon. So, if a negative charge is coming on oxygen, it is more stable compared to the carbon because oxygen is having high electronegativity. So, this oxygen will attract this lone pair towards it. So, this negative charge will be kind of stable. but carbon is having less electronegativity compared to oxygen. So it will not be able to attract the electron pair as strongly as of oxygen. So if we are having two cases where there is negative charge on oxygen and carbon, the negative charge on the oxygen will be stable. Okay. So if we are comparing these three, in C, the negative charge is coming on oxygen. So the most stable one is C. So C is the most stable. First we got, now we have to find from A and D, which is most stable. Okay. So if you are looking at A, this negative charge can delocalize between two carbonyl. It can either move here, it can either move here. So delocalization is present. In B also, it can either move here, it can either move here. But there is additional influence of one phenyl ring. So how the phenyl ring will influence? We have to see. Due to this phenyl ring, this double bond can move here. In that case, this will move here. In this side also, due to the presence of a phenyl ring here, this double bond can move here and this will move here. So if we are looking at the carbonyl carbon, in first case, there is no group here. There is no additional conjugation from this side. So this carbon is electrophile. It is having a positive charge, partial positive charge due to the electronegativity of oxygen. But if we are looking in the second molecule, due to the influence of a phenyl ring here, this double bond can also move here. In that case, the partial positive character of this is less compared to first case, because in first case there is no conjugation, only conjugation from this side, right? But in second case there is conjugation from this side and there is conjugation from this side. In first molecule only delocalization of this negative charge, but in second molecule there is delocalization of this negative charge plus phenyl ring. That will make the delocalization of this negative charge less. So the acidity of first molecule will be higher. Then comes second molecule. So the order will be C greater than A greater than B. So this is the acidity order. In question, the correct order of acidity they have asked. So in option C, that is C greater than A greater than B. Option C is the correct answer. Okay. So now we have discussed both acidity and basicity. Now we'll discuss general concepts in organic chemistry. So in organic chemistry, reactions are happening by the attacking reagent, which will attack on an organic molecule. And first we'll get intermediates. From these intermediates, we'll get products and byproducts. Okay. So it all, every reaction will happen by the attack of an attacking reagent in a organic molecule or substrate. Now the attacking reagent are of two types. Either it can be electrophile or it can be nucleophile. So first we'll discuss about electrophile. So electrophile, from the name itself we can see electrophile is, electro means electron, phile means lover. So this molecule is electron lover. Means this molecule is an electron deficient molecule. Due to the deficiency of electron in this molecule, that's why it loves electron. So this molecule will attack the nucleophilic center or electron rich center in our substrate and we'll get the product. And the electrophile can be of two types. Either it can be a positively charged electrophile or it can be a neutral electrophile. So now we'll discuss about two types of electrophile. One is positively charged and one is neutral electrophile. I will give you an example. For positively charged electrophiles, either NO2 plus, Cl plus, CH3 plus, all these are example of positively charged electrophile. And for neutral electrophile, AlCl3, BF3, CO2, SO3, all of these are example of neutral electrophile. Now we'll see how each of these molecule is becoming electrophile. First we'll take NO2 molecule. And this is the structure of NO2. There is a positive charge on nitrogen. And if you are counting the total number of electrons around nitrogen here, total, there are 4 bonds and 2 electrons in each bond, so total 8 electrons. So there is 8 electrons around the nitrogen, but still it is electron deficient. Why? Because here the nitrogen is attached to electronegative oxygen and this oxygen will attract the electron pairs towards it. That's why this nitrogen is electron deficient. That's why it is electrophile. Now we'll take the CH3 plus. In CH3 plus, there are 3 CH bond and 1 positive charge. If you are counting total number of electron here, total 3 sigma bond. So 3 into 2, total 6 electron. So this molecule need 2 more electron to complete its octet. So due to the deficiency of these 2 electron, this molecule is an electrophile. So now we'll see in case of neutral electrophile. First we'll take AlCl3. There is an aluminium and 3 chlorine attached to the aluminium. And if we are counting the total number of electron here, total 3 bonds into 2, so total 6 electron. Again, aluminum need 2 more electron to complete its octet. So that's why this AlCl3 is electron deficient. And to add to this factor, there is a vacant p orbital in the aluminum that make this molecule more electrophile. Okay. In the case of VS3 also, this is the structure of VS3. Again, there is only 6 electrons. So this molecule need 2 more electrons to complete its octet. And there is a vacant p orbital in the boron, which will make the molecule more electrophilic. Now we'll see what is happening in case of CO2. So here this is structure of CO2. Here if you are counting total number of electrons, 4 bonds into total 8 electrons are there and there is no positive charge, but still it is electrophile. Why? Because this carbon also attached to 2 oxygen atom, which is electronegative. So that's why this oxygen will attract electron pairs towards it and this carbon will become electron deficient and it will become electrophile. Okay. So we have seen what is electrophile and there is 2 types of electrophiles are there. One is positively charged electrophile, one is neutral electrophile. All of these are electron deficient and this will react with a nucleophilic center or electron rich center in a molecule in an organic reaction. Okay. Now we will see the second type of attacking reagent, that is nucleophile. So nucleophile is a molecule that brings electron pair in a reaction. That means there is this excess electron in the nucleophile and it acts as an electron donor in the reaction. So nucleophile is a substance that brings electron pair and it is having excess electrons. So that's why it is acting as an electron donor in the molecule and it will attack the electrophilic center or electron deficient center in the molecule. Suppose if we are comparing both electrophile and nucleophile, it will be exact opposite to each other. In electrophile, we have seen it is a electron deficient molecule, but nucleophile is electron rich molecule. And in a reaction, electrophile will attack electron rich center in substrate, but nucleophile will attack electron deficient center in molecule, right? So now we have to explain different type of nucleophiles. There are 3 different type of nucleophile. The first one is negative, is neutral nucleophile, and the third one is ambident nucleophile. Okay. So there are 3 different types. The first one is negative nucleophile, the second one is neutral nucleophile, and the third one is ambident nucleophile. So for the negative nucleophiles, the examples are OH minus, RO minus, H minus, all this. In all these molecules, we can see the excess charge present in the molecule. So here, this negative charge is acting as the nucleophile. The OH minus is called hydroxide ion and RO minus is called alkoxide ion and H minus is called hydride ion. Okay, in all these, the excess negative charge will act as the nucleophile. In neutral nucleophile, the examples are NH3, H2O, ROH kind of molecule. In all these molecules, there is no charge. Instead, we can see the lone pair of electron in this molecule. For example, if you are looking at the structure of NH3, there is a lone pair present on the nitrogen. This lone pair will act as the nucleophile. In H2 also, if you are looking at the structure, there is 2 OH bond and there is 2 lone pair on the oxygen. These lone pairs will act as the nucleophile in case of H2O. Okay. Now there is ambident nucleophile. Ambident nucleophile means the nucleophile where there is 2 nucleophilic atoms in the molecule. Example is cyanide or CN. Here the structure is C triple bond N. Here both carbon and nitrogen can act as the nucleophile. And one more example is thiocyanate ion or SCN minus. Here also both sulfur or nitrogen can act as the nucleophile. So this is the different type of nucleophile. There is negative, neutral and ambident nucleophile. So as of now, we have discussed what is electrophile. So electrophile is an electron deficient molecule which will attack the electron rich center in the substrate. There is 2 types, either positive charge or neutral electrophile. These all molecules are electron deficient. Then there is nucleophile. Nucleophile is having excess electron, and that's why it will act as an electron donor, and it will attack the electron deficient center in the substrate. And there are three types: negative, neutral, and ambident nucleophile. We have seen an organic molecule will react with the attacking reagent. It can be either electrophile or nucleophile. Then we first will get an intermediate in the reaction. From this intermediate, we will get the product. So now we have to explain the intermediate. Until now, we have seen that in an organic reaction, an organic molecule will react with a reagent. Either it can be electrophile or nucleophile. And first, we will get an intermediate. From this intermediate, we will get our ultimate product. Okay. So intermediates are molecules or species which formed between reactant and molecule, and this will be reactive and unstable. Okay. So intermediates will be unstable and reactive. In organic chemistry, mainly there are 5 different types of intermediates. The first one is carbocation, and there is carbanion. The third one is free radical. There is nitrene and also carbene. The fifth one is carbene. Okay. These are the 5 different types of intermediates. First one is carbocation, then there is carbanion, free radical, nitrene, and carbene. So in this class, briefly, we'll discuss about these 5 different intermediates. Okay. So the first one is carbocation. And here in the name itself, carbo means carbon, cation means positive charge. This means that in the molecule, there will be a carbon with positive charge, and this type of molecule is called carbocations. An example for this type of molecule is CH3 plus, and this will call as methyl carbocation. Now we'll see a reaction which will result in the formation of a carbocation. Suppose this reactant, that is CH3CH2I, is reacting in our molecule, and this bond is breaking between CH2 and iodine. What will happen? If we are taking both carbon and iodine, we know the electronegativity of iodine is very much high compared to the carbon. So the bonding electrons will move to the iodine instead of carbon, right? So if this bond is breaking, this bonding electron will move to the iodine, and this will result in the negative charge on the iodine and positive charge on the carbon. So what will be the product we will get from this cleavage? We will get CH3, CH2. There will be a positive charge on the carbon plus I minus. And here you can see there is a positive charge on the carbon, and this is an example of carbocation. So now we will discuss about carbanion. The second type of intermediate is called carbanion. Here also there will be a carbon atom, and there will be anion means negative charge. So in molecule there will be a carbon atom with negative charge. An example is the CH3 minus. Okay. And third type of intermediate is free radical. In free radical, there will be unpaired electron either in atom or molecule. And these are highly unstable, and this will be very reactive also. So suppose the Br2 molecule is interacting in UV light. What will happen to this? So if Br2 molecule is interacting in UV light, the bond between both Br atoms, in a bond, there will be 2 electrons, right? So the bond between 2 bromine atoms will leave homolytically. That means one electron will move to one of the bromine, and second electron will move to another bromine, and we'll get 2 bromine atoms with unpaired electron. And this type of atoms or molecules are called free radicals. So there can be chlorine radical, bromine radical, iodine radical, and methyl radical, ethyl radical. All these are possible in an organic reaction. And these are the different examples of a free radical: chlorine, bromine, iodine, methyl, ethyl radical. All these are possible. Okay. So this is a third example of intermediate. And the fourth one is carbene. So carbene means in our molecule there will be a carbon with a lone pair. That is what is meaning by a carbene. Suppose a molecule like CH2N2 is reacting, then this will release N2, and we will get CH2 with a carbon with a lone pair, and this is called carbene. And the last intermediate that we are going to discuss is nitrene. Here there will be a nitrogen with 2 lone pairs and a bond pair. Like this, you can see a nitrogen in our molecule with 2 lone pairs and a bond pair. This is the last intermediate. So as of now, we have discussed 5 different intermediates. The first one is carbocation, carbanion, and then there is free radical and carbene, and fifth one is nitrene. So now we have seen 5 different type of intermediates. In this class, we briefly discussed about this, and in the coming chapters of reaction mechanism, we'll discuss detail about this. So as of now, we have seen both electrophile and nucleophile, and we have discussed about intermediates also. So now we need to know if in an organic reaction, if we are seeing either electrophile or nucleophile, we need to know in our organic molecule where this attacking reagent will attack. For that, we need to know about different electronic effect. So next we are going to discuss about different electronic effect in a organic molecule. So mainly there are 4 different type of electronic effect. The first one is inductive effect, and there is resonance effect, then there is hyperconjugation, and last one is electromeric effect. These 4, the first 3 are permanent effect, and the electromeric effect is temporary effect. Okay, so why we are discussing about this electron displacement effect? Suppose this is a molecule, and in this molecule there can be both positive charge and negative charge, and the attacking reagent may be either electrophile or nucleophile. So we need to know where this electrophile and nucleophile attack. We know electrophile will attack the electron rich center, and nucleophile will attack the electron deficient center. So to know where in a molecule positive charge and negative charge will arise, and to know where the nucleophile and electrophile attack, we need to explain about different electron displacement effect. First electron displacement effect is inductive effect. So the inductive effect we will denote using I. This will explain using a molecule. Suppose this is a molecule. Here we can see a carbon-fluorine bond. And if you are looking at the bond between carbon and fluorine, this bonding electron will move slightly towards fluorine due to the high electronegativity of fluorine. Here we know the electronegativity of fluorine is high compared to the electronegativity of carbon. Due to the high electronegativity, the bonding electron of this carbon and fluorine bond will move closely to fluorine. And there will be a partial negative charge on the fluorine, a partial positive charge on the carbon due to the electron movement of this bond towards fluorine. And this fluorine will influence the second carbon, that is this carbon also. But this influence will be less because here the fluorine is not adjacent. It is somewhat far compared to this carbon. So here the inductive effect will be there, but compared to the first carbon, it will be less. So now he will denote it using 2 arrows, and here also a partial positive charge will come, but compared to the first carbon, again that positive charge will be less. That will denote using partial positive. Okay, now the fluorine will influence this carbon also, but compared to these 2 carbon, the inductive effect of fluorine on this carbon will be again less. So that will denote using 3 arrows, and due to the inductive effect of fluorine on third carbon, there will be a partial positive on the third carbon. Okay, so what we have seen here, it is a distance dependent effect. That means as the distance increases from the substituent, the effect is decreasing. Okay, and this is a permanent effect also. If a substituent present on a carbon chain, that means that effect will be there as long as the substituent there. So it's a permanent effect and it's a distance dependent effect also. Now there are 2 types of inductive effect. Either it can be plus I effect or it can be minus I effect. Plus I effect means here a electron donating group is attached to the carbon chain. A minus I effect means here a electron withdrawing group is attached to the carbon chain. And to understand about this plus and minus charges, you think about a carbon attached to a substituent. If the carbon is losing the electron, like the electrons are moving towards the substituent. Here, if you are thinking about this carbon is losing electron, right? So that will denote using minus I. And suppose the electrons are moving towards our carbon, that means if you are thinking about carbon, in this case, carbon is getting electron density. So carbon is getting means positive. So in this case, it will denote using plus I. So minus I means the electrons are moving away from the carbon chain, and plus means carbon chain is getting electrons. Okay, that's how we'll remember the plus I and minus I effects. So plus I means electron donating groups are attached to carbon chain, and minus I means electron withdrawing groups are attached to carbon chain. Okay, so the example of electron donating groups are methyl, ethyl, propyl. All these groups are electron donating group, and any group which will have electronegativity higher than that of electronegativity of carbon will have electron withdrawing effect, and it will have minus I effect. Okay, In this case, minus I effect, what will happen? The electron density of this CX bond will move towards the X substituent. But in case of electron donating group, this will move towards our carbon chain. Okay. Now we will see the application of inductive effect. Here we can use this to explain the stability of carbocation and carbanion. Suppose we have a carbocation like this, and we have one more carbocation. Here the only difference is that instead of one CH3, there is a hydrogen group. So we need to know which one of this is more stable. So if you are looking at both molecules here, in the first molecule you can see 3 methyl group. So here we have already seen methyl groups are electron donating group. It is a plus I group. So it will give electron density to the carbon. So the arrow will be towards carbon. All these are plus I groups. This also plus I, this also plus I, this also. So 3 methyl groups giving electron density towards the carbocation. So to check the stability of carbocation, what do we have to know? We need to check the positive charge on the carbon cation is getting reduced or not. If the positive charge on the carbocation is getting reduced by the electron movement, then that carbocation will be more stable. So if you are looking in this molecule, there is a carbocation and 3 methyl groups are giving its electron density to this carbocation. So this positive charge is getting reduced. In the second molecule, here also we have a carbocation. Here there are 2 methyl groups which will give its electron density due to the plus I effect, and the direction will be like this. But compared to the first molecule, there are only 2 methyl group. In first molecule, there are 3 methyl group. So stability of carbocation will be higher in first case compared to the second case. Now we can use the inductive effect to know the stability of carbanion also. So carbon having a negative charge is called carbanion. So this is the first molecule. We'll compare the stability of this carbanion with one more carbanion. In the second carbanion, suppose one CH3 group is less. Instead of that, one hydrogen is there. So we need to know which one of these carbanion is more stable. Okay. So again, we'll consider the inductive effect of both molecule. Here there are 3 methyl group. So these 3 will donate electron density through plus I effect. And in this carbon, the electron density will again increase. Right? In the second molecule, only 2 methyl groups. So these 2 methyl groups will donate electron density to this carbon. So the electron density of the carbanion will again increase. But if we are comparing both these molecules, in first molecule, there are 3 CH3 group, so 3 plus I effect. In second molecule, only 2 CH3, so 2 plus I effect. So the electron donation in the first molecule is higher than the second molecule. Now we need to look at the stability of carbanion. Carbanion means there will be a negative charge. For this negative charge to be stable, there should be less intensity of negative charge. If there is intensity of negative charge is again increasing by the donation of other group, then it will become less stable. If there is a electron withdrawing group in a molecule, then the negative charge will become stable. Like we had discussed earlier, right? If there is a ketone adjacent to a negative charge, this negative charge will become more stable because here this negative charge intensity is getting reduced by the influence of carbonyl carbon. But if in a molecule there is a negative charge, and if groups are again putting electron density to this negative charge, that means the stability of carbanion will reduce. So we need to know which of the molecule the electron density will be less, that molecule will be, that carbanion will be more stable. So in first molecule, 3 plus A effect, so high electron density, so it will be less stable. Compared to the first molecule, in second molecule only 2 plus A effect. So compared to first molecule, the second carbanion will be stable because there is only 2 CH3 to give electron density to the carbanion. Okay. So that's how we'll determine the stability of carbanion and carbocation using inductive effect. Now we'll look into the stability of an acid in terms of inductive effect. So to know the inductive effect of groups in a stability of acid, we'll compare the acidity of this molecule with some other molecule. Suppose a similar type of molecule, but here instead of one chlorine, one hydrogen is present. Which acid will be stable, we have to see. So again, we'll use the inductive effect of fluorine atom here. So seen in the beginning of this lecture, for a molecule HA to be stable, we'll see the conjugate base, that A minus, and we'll determine in which case the A minus is more stable, that acid will be more strong, right? So here also we will follow the same thing. In both this molecule, we will lose a proton and we will get a conjugate base and we will determine the stability of this conjugate base. Whichever conjugate base is more stable, that will be the strong acid. Okay. So in first molecule, if we are losing a proton, the proton will lose from this OH group. Proton is losing from here, we'll get a negative charge on the oxygen. So we'll get a molecule like this. In the second molecule also, if you have to lose a proton, this bond will break and it will lose a proton and we'll get a negative charge on the oxygen. So now this is two molecules. Now we have to compare the stability of these two molecules. In the first molecule, there is a negative charge in a molecule. So we have seen in earlier case also, if there is a negative charge in a molecule, if there are groups in a molecule which is able to attract this electron density towards it, then that molecule will become stable. Right? So here also a negative charge. So we have to see in which molecule the electron density is getting accepted by other groups in the molecule. So in first case, there are chlorine groups. So chlorine groups we have seen it is having minus A effect. Minus A effect means it will accept the electron density towards it from the carbon chain. So here this will accept the electron density through minus A effect. This chlorine also will do the same through minus A effect, this chlorine also. So there are total 3 minus A effect in the first molecule, and these 3 minus A effect will take part in the stabilization of this negative charge. In the second molecule, there is only 2 chlorine. So there is 2 minus A effect. So these 2 minus A effect are taking part in the stabilization of this negative charge. So to compare both these, in first molecule, there are 3 minus A effect. In second molecule, there is only 2 minus A effect because there is only 2 chlorine atom. So the negative charge is more stabilized in the first molecule. So the acidity of first molecule is higher than that of the second molecule. Okay. Now using the inductive effect, we can find out the basic strength of different molecules. So here in this molecule, we can see a nitrogen and we can see a lone pair on the nitrogen. And we will compare the basicity of this molecule with a similar molecule in terms of inductive effect. Suppose instead of a CH3 group here, a hydrogen is present. So basic strength we have seen in the beginning, we can express in terms of two. First, availability of lone pair. If there is highly available lone pairs, then that molecule will be highly basic, right? So if we are comparing both these molecules, in both molecules, nitrogen is there, lone pair is there, both are basic. For a molecule to be basic, it should be able to donate the electron pair, right? Then only it will become basic. So in first molecule, there are 3 CH3 group. All 3 will take part in the plus side effect that this CH3 will donate its electron density towards the nitrogen. So in the electron density in nitrogen will get increased in the first case. In the second case, 2 CH3 will take part in the plus side effect and again the electron density on the nitrogen will get increased. If high electron density in the nitrogen means highly available lone pair, it can donate its lone pair easily. That means highly basic. So to compare both first and second molecule, first molecule 3 CH3 group, that means 3 plus I effect. So high electron density on the first nitrogen than the second nitrogen. That means the basic strength of first molecule will be higher than that of second because of the plus I effect of 3 CH3 group in the first molecule. Okay. So that's all we have to discuss about inductive effect. Now we will see the second electronic effect, that is resonance effect. Here the resonance effect will denote using R. Here the resonance effect means is the possibility of shifting a pi electron. Okay. It's the possibility of shifting pi electrons in a molecule is called as resonance, and resonance will result in the highly stability of our molecule, and the necessary condition for resonance to occur is the conjugation. If there is a conjugation in molecule, then there will be resonance. So what is conjugation? Conjugation means delocalization of electrons, right? So there are different type of conjugation. Suppose we have two double bonds separated by a single bond. It is an example of conjugation. And we have a double bond which is attached to an atom which is having lone pair. This is also an example of conjugation because here this can take part in the delocalization. Now a double bond separated by a carbon having a positive charge. This is also an example of conjugation because this electron can move here. And All these are example of conjugation, and conjugation is the necessary condition for resonance. And resonance will result in the high stability of the molecule. Okay. Now, like inductive effect, we have seen inductive effect is of two types, plus I and minus I. Resonance effect is also of two types, plus R and minus R. Here, if the pi electrons are moving away from the atom, suppose we have a carbon chain and we have a substrate. If the pi electrons are moving away from our carbon chain, it will have minus R effect. It is same as of inductive effect. Inductive effect, what you have seen, suppose a carbon chain is there and a substance is attached to carbon chain. If the electrons are moving away from the carbon chain, we call it as minus I effect. If the electrons are moving towards the carbon chain, we call it as plus I effect. Here also the same thing. If the electrons are moving away from the carbon chain, we'll call it as minus R effect. If the electrons are moving towards the carbon chain, we'll call it as plus R effect. Okay. And now we'll give example for both plus R and minus R. Suppose we are having an NH2 group attached to a benzene ring. In this case, it is an example of plus R effect. So plus R effect we have seen, it is the movement of pi electron towards the carbon chain. So here we can see the two lone pairs on the nitrogen will move towards the carbon chain, and we'll get the resonance structures like this. And it is an example of plus R effect because the electron are moving towards the carbon chain. Now for the minus R, suppose a nitro group is attached to the benzene ring. What will happen here? The electron density will move from benzene ring to the substrate. That is benzene ring to the nitro group. In this case, it is an example of minus R effect. As you have seen, if the electron density is moving away from the carbon chain, it is called as minus R. So if nitro group is attached to a benzene ring, it will result in the minus R effect. And all the structure are result of the resonance of nitro group with the benzene ring. Okay. So the resonance effect, that is the second electron displacement effect also we have explained. Now the third electron displacement effect, that is hyperconjugation. Now hyperconjugation is the delocalization of a sigma electron to an adjacent pi bond or an adjacent p orbital. Okay, this is what is meaning by hyperconjugation. Suppose we have C double bond C in our molecule, and adjacent to that we have a carbon which is having hydrogen, and the carbon adjacent to the C double bond C, we will call it as alpha. So if there are hydrogen in alpha carbon, that means there is a possibility for the hyperconjugation. How it will happen? This CH bond will break, and this bonding electron will move in between these two carbon, and this bond will break, and you'll get a C double bond C and a negative charge on this carbon. Okay, so this is what is meaning by hyperconjugation. Here it is an example of sigma pi conjugation, because if you are looking, this bond, a sigma bond is breaking and a pi bond is also breaking. So it is an example of sigma pi conjugation, and this will also call as no bond resonance, because this is also an example of resonance, but there is no bond between carbon and hydrogen in the product. So that's why it is called as no bond resonance. So we have explained hyperconjugation as the delocalization of sigma electrons to a pi bond or to an empty p orbital. So the first case is this one. The sigma electrons are delocalized to a pi bond. The second case is, suppose again we are having an empty p orbital in a molecule, and adjacent to that, that is alpha carbon, hydrogens are present. In this case, what can happen is this CH bond again can break, and this bonding electron will move to the empty adjacent p orbital. And in that case, we will get a product like this. We'll get a carbon double bond carbon in the product. So this is what is hyperconjugation. It is the delocalization of sigma electron to an adjacent pi bond or an empty p orbital. That means that this hyperconjugation is present in both alkene and empty p orbital means carbocation. This also means that hyperconjugation can be used to explain the stability of both alkene and carbocations. Okay, that we'll see. And suppose there are alpha hydrogen in our molecule. In that case, there is a possibility of hyperconjugation. Higher the number of alpha hydrogen, higher will be the hyperconjugative structure and higher will be the stability of the molecule. So if the number of alpha hydrogen is increasing, the stability of our molecule will also increase. This we'll see in case of both alkene and carbocation, because in these two cases, hyperconjugation is possible. Okay, first we'll see in case of alkene. We have to see which of the 4 alkene is most stable, and we have to find the stability order. Okay. To determine the hyperconjugative structure, we need to look at the alpha hydrogen. If n number of alpha hydrogen present, that means n number of hyperconjugative structure is possible for our molecule. So for the first molecule, to determine the hyperconjugative structure, we look at the alpha hydrogen. So this is the alpha hydrogen that is adjacent to C double bond C. Here 3 alpha hydrogen, that means 3 hyperconjugative structure. In the second molecule, here there is 2 alpha carbon, this carbon and this carbon, and there is 3 alpha hydrogen in this carbon, and there is 3 alpha hydrogen on this carbon. So total 6 alpha hydrogen is present in the second molecule. In the third molecule, we can see 3 alpha carbon, 1, 2, 3. In all of the alpha carbon, there are 3 alpha hydrogen present. That means total 3 into 3, that is 9 alpha hydrogen present in the third molecule. And now in fourth molecule, there are 1, 2, 3, 4. That is 4 alpha carbon. That means 4 into 3, total 12 alpha hydrogen present. So we know if n number of alpha hydrogen, there is n number of hyperconjugative structure, and higher the number of hyperconjugative structure, higher will be the stability. So the fourth molecule is having 12 number of alpha hydrogen, means it is having highest number of hyperconjugative structure. So the fourth molecule will be most stable. Then comes 3, then comes 2, then comes 1. Okay. So this is the stability order of this alkene. Now we'll look in case of cation, that is carbocation. If you have to compare stability of both these atoms, we have already discussed the stability of these two molecules in terms of inductive effect, right? Here, this 3 CH3 are donating electron density to this carbocation through plus I effect. So the electron deficiency of this carbon atom is less compared to this molecule, because here only 2 CH3 are donating electron density to the carbocation. This we have seen in case of inductive effect. Now we'll explain the stability of both these molecules in terms of hyperconjugation. So to explain the stability through hyperconjugation, we need to look at the alpha carbons. So here 1, 2, 3. Total 3 alpha carbons are present. 3 alpha carbon means in every alpha carbon there is 3 hydrogen. So total 3 into 3, total 9 alpha hydrogen present in the first case. In second molecule, there are 2 alpha carbon. In both alpha carbon, there are 3 hydrogen. That means total 6 alpha hydrogen present in the second molecule. So higher the number of alpha hydrogen, higher is the hyperconjugative structure, higher will be the stability. So if you are comparing both the molecule, first molecule is having higher number of hyperconjugative structure. So first carbocation is more stable. The stability of this molecule is through two effect, plus I effect and hyperconjugative effect. Now we'll see the last electron displacement effect, that is electromeric effect. Here, the electromeric effect is the transfer of pi electrons of a multiple bond when attacking reagent attacks the double bond. That is electromeric effect. Suppose there is a double bond in our molecule between A and B. If a reagent is coming, the electron displacement is explained due to the electromeric effect. This effect will only valid when a reagent comes. If there is no reagent, then there is no electromeric effect. That's why this displacement effect is a temporary effect compared to other 3 effects. Okay. So suppose there is a double bond B present in a molecule, a reagent is coming. Either the reagent can be of positive charge or negative charge. And suppose the electronegativity of B is higher than that of electronegativity of A. So for this reagent to react with the double bond, this double bond has to break. So suppose electronegativity of B is higher than that of electronegativity of A. In that case, this bond will break towards A. So you'll get positive charge on the atom A and negative charge on the atom B, since the electronegativity of B is greater than that of electronegativity of A. So this will get, and according to a reagent, whether it is plus or minus, it will react with either A or B. So just like inductive effect and resonance effect, electromeric effect is also 2 types. It can be either plus C effect or minus C effect. We'll see both effects. Now, plus C effect means, suppose in our molecule, a double bond B is present and electrophile is coming as the attacking reagent. So we have seen the electronegativity of B is greater than that A. Then what happens? This bond will break and A will get a positive charge and B will get a negative charge. And in this case, if electrophile is coming, this electrophile will attack with the B. If you are looking here, both electron move to atom B and electrophile also attack to atom B. Both are happening to atom B. This is called plus C effect. So if both electron displacement and attacking reagent is going to the same atom in a double bond, it is called plus C effect. Now we can explain minus C effect. It is the opposite of this. Again, there is a double bond in our molecule. Suppose the electronegativity of B is greater than that of electronegativity of A. In this case, here nucleophile is coming. So nucleophile is having a negative charge. Again, this bond will break to B due to the high electronegativity of B. So you'll get a positive charge on A and negative charge on B. Since in this case, a nucleophile is coming, it is having a negative charge, right? So it will react with the positive charge. So it will react with A. See effect, the electron displacement is happening to one atom and the attacking reagent is going to the another atom. Both are happening to the different atom. This is called minus C effect. And plus C effect will happen if positive charged species are coming to our molecule, and minus C effect will happen if nucleophile or negative charged species are attacking our molecule. Okay. So this is the last electron displacement effect, which is a temporary effect, which will only happen if a reagent comes. Otherwise, there is no electrometric effect. So as of now, we have explained different type of electron displacement effect. We have explained inductive effect, that is I effect. It can be either plus A effect or minus A effect. And we have explained resonance effect. Again, it can be either plus effect or negative effect. Then we have explained hyperconjugation effect. Then we have explained electromeric effect. That also either can be positive or negative effect. So suppose in a molecule, more than one of this electron displacement effect is coming, then the more dominant effect will be resonance effect, then comes hyperconjugative effect, then comes inductive effect. We have to remember this order because if we have to determine the stability of molecule by means of more than one electron displacement effect, then the most dominant effect will be resonance. Then comes hyperconjugation, then comes inductive effect. So now we'll discuss the difference between resonance and tautomerism. Resonance we have seen in this class already. Resonance is a delocalization of electron. In resonance, there is no movement of atom. It's a different representation of the same compound. That we have seen in today's class. If you are looking at the different resonance structures of aniline, here these electrons are moving towards the benzene ring. Then the electrons are moving through entire benzene ring and it is coming back to a amine group. Here, if you are looking, only electrons are moving. There is no movement of atom. If you are looking at the resonance structures of nitrobenzene also, here the electrons are moving towards the nitro group. Then all this resonance structure we are getting by the movement of electron. There is no movement of atom in any of these structures. So resonance means it is the delocalization of electron. There is no movement of atom. But tautomerism, it will involve the movement of atom. It is a form of isomerism where a single compound can be exist in a two or more interconvertible structural forms. That is what is meaning by tautomerism. So this is the difference between resonance and tautomerism. In resonance, only electrons will move, but in tautomerism, there will be a movement of an atom. So to find out the difference between resonance and tautomerism is, if only electrons are moving, it is resonance. If atom is also moving, it is called tautomerism. Okay. One example is the keto-enol tautomerism. So here, if both hydroxy group and double bond is coming on the same carbon, bonding electron between oxygen and hydrogen can move between oxygen and carbon. In this case, we will get a double bond between oxygen and carbon, and the hydrogen will move to this carbon. This is an example of tautomers. So this is tautomerism. Now we will move to the homo-LUMO concept in organic chemistry. We have already seen it is the highest occupied molecular orbital and LUMO is the lowest unoccupied molecular orbital. And in organic chemistry, there are different molecular orbitals. There are sigma, pi, then non-bonding orbitals, then comes pi star and sigma star. These are the different molecular orbitals in organic chemistry. Suppose we have a CO bond in our molecule and we have to represent this in terms between carbon and oxygen, there is a sigma bond. So there is a sigma orbital. If there is a sigma orbital, then there will be anti-bonding sigma, that is sigma star also will be there. And here there is an oxygen, and in oxygen we know there will be lone pair. If lone pair is present in our molecule, there will be non-orbital, that is NP. So here there will be electron in sigma orbital because of this bond, and due to the lone pair on oxygen, there will be electron in non-bonding orbital also. And now if you have C double bond O bond in our molecule, here we have sigma bond between carbon and oxygen. So there will be a sigma orbital. If sigma orbital is there, there will be a sigma star orbital also. And there is a pi bond between C and O. That means there is a pi orbital. If pi orbital is there, that means pi star is also there. And since there is oxygen, there will be lone pair on oxygen. So that means there is a non-bonding orbital also. So in sigma bond, there is 2 electrons that we will put in a sigma orbital. In pi bond also 2 electrons that we will put in the pi orbital. In oxygen lone pair, we will put in the non-bonding orbital. Okay. So this is the molecular orbital representation of C double bond O. In an organic reaction, the electron has to move from one orbital to another orbital, right? Here, in organic reaction, the electron will always move from HOMO of one orbital to the LUMO of another orbital. Okay? We'll see how the electron will move from one orbital to another orbital and how the bond breaking and bond forming will happen. Okay? So we'll start with hydrogen. Suppose we have H2 molecule here. H2 molecule, there is a single bond between both hydrogen atoms. H2 formed by the bonding between two hydrogen atoms. So in hydrogen atom, we will put the electron configuration in terms of 1s1, 2s1 like that. So since in hydrogen only one electron, we'll put just 1s1. But in molecules, we'll represent the electron configuration in terms of sigma, pi, sigma star, pi star. So here in H2 molecule, there are 2 electrons. We put that in sigma 1s orbital, that is 2 electron. Okay. So the sigma 1s will draw how the sigma orbital formed by the combination of 2 hydrogen atomic orbital. So one hydrogen is here, another hydrogen. Both these are combined to form a sigma orbital and a sigma star orbital. So here, this is 1s orbital of first hydrogen, 1s orbital of second hydrogen. Both these combined to form a sigma 1s orbital, which is bonding orbital, and there is a sigma star 1s, which is an anti-bonding orbital. Since there is only single bond between both these hydrogen, single bond means 2 electron will be there. These 2 electron we can put in the sigma 1s orbital. Now the bond order we will see using bond order is equal to half into bonding electron minus anti-bonding electron. Right? So here the bond order equal to half into the number of electron in bonding orbital is 2 minus there is 0 electron in anti-bonding sigma star, so 0. So 2 by 2 which is equal to 1. That's how the bond order came for H2 molecule as 1. Suppose we need to break the sigma bond between these 2 hydrogen. What we have to do? To break the sigma bond between these 2 hydrogen, we can put 2 electron in the sigma star orbital. In that case, what will happen? Here, again we'll find the bond order. Here the bond order equal to half into number of bonding electron, that is 2 electron minus number of anti-bonding. Here now 2 electrons are there in anti-bonding. So 2 minus 2, it is 0. So bond order will be 0. That means this bond between both hydrogen has broken now. That means to break a sigma bond, what we have to do? We have to put electron in sigma star orbital. To break a pi bond, what we have to do? Put a electron in pi star orbital. So whatever bond we have to break, we just need to put electron in the anti-bonding orbital. If you are putting electron in anti-bonding orbital, the corresponding bond will break. Now we will see what is actually happening in case of organic molecule when the reaction is happening. How the electron transfer is happening from HOMO to LUMO. So we have discussed that electrons will always transfer from HOMO of one molecule to the LUMO of another molecule, right? Suppose this reaction is happening. Here, the OH minus is reacting with the molecule and we are getting a product here. How the reactions happened? Here, the non-bonding electron in the oxygen is reacting with this carbon. In that case, the carbon iodine bond, that is this bond is being broken and we are getting a product like this. Here we can see the negative charge attack the Ci bond and Ci bond has broken. In this case, if one bond is broken, I told you if sigma bond is broken, that means electron has moved to the sigma star orbital. So in this case, if Ci bond is broken, that means electron has moved to the antibonding sigma star Ci orbital. So electron has moved to the antibonding sigma star Ci orbital. Now we have to find out from where this electron came. Electron came from oxygen, right? So if electrons are coming from either lone pair or negative charge, it will be from non-bonding electron. So either if electrons are coming from either negative charge or lone pair, that means that these electrons are coming from non-bonding orbital of that corresponding atom. Here, the electrons are coming from the negative charge on the oxygen. That means electrons are coming from non-bonding orbital of oxygen. Okay. So in this reaction, the electrons moved from non-bonding orbital of oxygen to the sigma star orbital of Ci bond. So to summarize what we have told in this section, for an organic reaction to happen, an interaction between HOMO of one molecule should happen with the LUMO of another molecule. In an organic reaction, here electrons are moving from a donor atom to the acceptor atom, right? Here in donor atom, HOMO orbital will interact. In acceptor atom, LUMO orbital will interact. Okay. So now we are going to see what is the HOMO orbitals in different cases, what is the LUMO orbitals in different cases. In donor atom, there are three cases. The electron can donate from either a sigma bond, pi bond or non-bonded, right? So we'll discuss each cases. Suppose in a donor molecule, there are two atoms, A and B. Suppose the electron density between a single bonded B is taking part in the reaction. That means the electron density between A and B is the HOMO here. In that case, the HOMO orbital will be sigma AB because there is only sigma bond between A and B and the sigma electrons are participating in these cases. So in this case, HOMO will be sigma AB. So in second case, in donor atom, A double bond B is present. In this case, the pi electrons are participating in the reaction. In that case, if pi electrons are participating, the HOMO will be pi AB because now the pi electrons between A and B is taking part in reaction. Suppose the non-bonding electron, there is a AB bond and there is a non-bonding electron on B and these non-bonding electrons are taking part in the reaction. That means the HOMO will be non-bonding orbital of AB. Okay. So we have seen three different cases of HOMO. The electron in sigma bond is donating, that means a sigma will be HOMO. If an electron in pi bond is donating, in that case HOMO will be pi of that bond, and if electron in lone pair is donating, in that case NB will be the HOMO. So now you'll see the different cases of LUMO. Suppose now we'll find out LUMO by looking at which bond is getting broken in the product. Okay. Suppose after the reaction A and B single bond is getting broken. In that case, here the electron are accepted to a sigma star orbital because that's why only a sigma bond between A and B broken. So here LUMO is sigma star AB. Suppose in the reaction, after the reaction, the double bond between A and B got broken. That means the electrons are accepted to the pi star orbital. In this case, LUMO will be pi star of AB. So this is the two different cases of LUMO. So now I will take different reaction and we will see from where to where the electrons are moving. This is the first example here. We know there is a lone pair in nitrogen. So the reaction will happen by the movement of lone pairs on nitrogen to this carbon. In that case, this bond will break and you'll get a NS3. Since the lone pairs on the nitrogen donated to carbon, there will be a positive charge on the nitrogen and there will be 3 hydrogen on the carbon. Now this bond broken. Okay. So now we have to see from where to where, from which orbital to which orbital electrons has moved. Here the electron donated by nitrogen from the lone pair. So that means the electron donated from a non-bonding orbital of NS3. This is our HOMO. Okay. Now to find out the LUMO, we'll see which bond has broken in the reaction. Here the Ci bond has broken. That means if a sigma bond is broken, that means the electrons are moved to the sigma star orbital, right? Here the Ci bond, the sigma bond I is broken. That means the electrons are transferred to the sigma star orbital of Ci. Okay. So the LUMO will be sigma star orbital of Ci. So now in this case, we have to see from where to where electrons are moving. So here there is a lone pair on phosphorus and this lone pair will attack this carbon and this bond will break. At the end, you'll get me. Since the lone pairs on the phosphorus attack the carbon, there will be a positive charge on the phosphorus. Now, the lone pairs on the phosphorus, the electron in the HOMO, that means it is a non-bonding orbital of pph3. Okay? So, this is our HOMO. And to find out the LUMO, we'll see which bond has broken. Here, the MEI, that is Ci bond has broken. That means the electrons are moved to the sigma star orbital of carbon and iodine. Okay, so this is our LUMO. Now we'll see in this molecule, the pi electron will take this H plus. In that case, this bonding electron will move to the bromine. So we'll get, if these pi electrons are moving, it will create a positive charge here, and this is taking hydrogen, so the hydrogen will come on this carbon. Now we have a Br minus also in the reaction mixture. Now this Br minus will come and attack this carbocation. This is second step. In the first step, what is happening? These pi electrons are attacking the H plus. Here we need to find from where to where the electrons are moving. So the first step is movement of pi electrons. Now the electrons in the pi bond took part in the reaction. That means here the HOMO is the pi orbital. Pi orbital between C double bond C is the HOMO in our molecule. Now the bond has broken in between HPR. That means LUMO is the sigma star orbital of HPR. Okay. Now we'll see a previous year question from this topic. CSIR June 2016. The frontier molecular orbital involved in the formation of carbocation intermediate in the reaction of isobutylene with HCl. So first we need to find out what is isobutylene. We know butane, right? The structure of butane is CH3, CH2, CH2, CH3. This is butane. This is a long chain alkane. Suppose one of the CH3 is coming as a substituent like CH3, CH, CH3, CH3. This will call as isobutyl. Here isobutylene. Lean means what? There is a double bond. Ene means in this molecule there is a double bond. There is a double bond between two carbons. So it will be like this. So this is a isobutylene molecule. Okay. So now we got isobutylene. We need to find out the HOMO and LUMO in case of reaction between isobutylene and HCl. So for that, we'll take isobutylene molecule first, which is CH3, C double bond, CH2 and CH3 is isobutylene. It will react with the HCl. What will happen? Reaction will happen. Here the pi electrons will take this H plus. Okay. So we'll get a product like here this hydrogen will come on this carbon and you'll get CH3 and you'll get a positive charge on this carbon. First step we'll get a carbocation and you'll get a Cl minus also. In second step, the Cl minus will attack this carbocation. That will happen in the second step, okay? But first step, we need to know from where to where the electron movement is happening. The HOMO orbital is this orbital, that is the pi C double bond C orbital, okay? And the LUMO is where the bond has broken. Here, the bond between hydrogen and chlorine has broken. Here, the sigma bond between hydrogen and chlorine is broken. That means the electrons are transferred to the sigma star orbital. So, LUMO is sigma star orbital of HCl. Now, we look at the option. So, in option first, they are giving HOMO and second, they are giving LUMO. Here, option A and B, pi of olefin, and option C and D are pi star of olefin. You'll see the answer is pi of olefin is the HOMO. So either A or B. Now we look at the LUMO. LUMO is the sigma star of HCl. That means option A is the correct answer. Here the HOMO is the pi of olefin and the LUMO is the sigma star of HCl. Okay. So electron has moved from pi orbital to the sigma star orbital, and that's how this reaction has happened in the first step. So we are winding up today's general organic chemistry class. So in this class, we have discussed first what is acids and bases. Then we went on to explain what is electrophiles and nucleophiles. Then we have explained different electron displacement effect. Then we have explained tautomerism, a small topic. Then at last of this class, we have explained the frontier molecular orbital concept or HOMO-LUMO concept. Okay, the HOMO-LUMO concept we will also call as FMO concept. And we have seen from where to where the electron will move in an organic reaction. So with this, we are winding up general organic chemistry class.